All right. Quick thing, participation. Some of you are almost done with participating point, but that doesn't mean you don't participate anymore. You're welcome to participate more. Some of you has not participated once. Okay, it's time for chocolate. Next time I'll bring my chocolate. So it would be +2 and a chocolate. So maybe energize yourself for participation.
Chocolate or Red Bull?
What's that?
Maybe Red Bull at 4 o'clock?
Oh yeah, of course. Aaron wanted the Red Bull so that everybody gets really hyper. So that's that. Okay, so we're moving into a new topic. We finished chromatography and we touched on spectroscopy a little bit when we did the LC lab. But now I'm going to talk more about the physics of it all. Of course, everybody loves physics. Nah, I know. We'll not dig too deep into physics, but just to understand the principle of spectroscopy and how we use it to quantify, analyze, identify, structure elucidation, all of that. Okay, so check knowledge, physics. The following are associated with a light wave. All right, hands up in the air, Erica. A and B. Agnes.
C.
What? C, only C?
Yeah.
Okay, Michelle.
A and C.
A and C, let's see, Drew.
What do you mean by associated?
What? What do I mean by associated? So they are related, like they're connected. So they're part of, they are part of the light wave. No? Components of the light.
All the way up to G.
Thank you, Aaron. It's all of the above. So there is the electromagnetic characteristics of light, and it's defined by the electric field and the magnetic field of the light wave. And then photon is pockets of energy that are carried by the light wave. And that's what I mean by associated. Still, okay, how do you describe it?
Well, light is part of the electromagnetic spectrum, and photons are like how you measure the energy in that.
Yeah, aren't they all associated with each other? How would you, okay, all right. How would you change this question?
I have no suggestion.
Oh, no, you can't do this to me. You can't tell me it's wrong and then you don't give me a suggestion. Think about it, then give me a suggestion later for next year. And I will change it based on your suggestion. All right. Following spectroscopy as means of analysis, detection can be based on Ray, no, Jenny, sorry, Ray. I think you're doing good with participation. A. Okay, anybody else? Vaidi? Anybody else? Other than Ben? Sven? Yes, A and B. So you can quantify absorption, you can quantify emission, and that would be fluorescence. So you can measure UV absorption, or you can measure UV fluorescence. Dissipation of heat, it does occur. So you have a ground state to excited state, and when you go back to excited state, some of the electrons or atoms or molecules dissipate heat. But you cannot measure that because it's so tiny, it cannot be detected. So you do get dissipation of heat in going from excited state to ground state, but you cannot really measure it in an increment that is sensitive enough for quantification. So the answer to that would be A and B. Okay, so after briefly checking the knowledge, we'll go into explaining what spectroscopy is about. So again, spectroscopy is a study of interaction between the electromagnetic radiation, which is the energy of light, with the matter. The matter can be based on the type of species you have. So depending on the species, you have different types of interaction. The species could be atomic, could be molecular. Some of you did the atomic absorption lab already, and that was interaction of the matter in the state of atom with light. Or it can be interaction of light with the molecule itself, not with the individual atom. So the interaction could be, like we said earlier, could be in the form of measuring absorption, could be in the form of emission of light, either absorption of light, emission of energy in the form of photon of light. It can be light scattering. This would be, we mentioned a little bit detector, one of the detectors in HPLCs are light scattering detector. So in this case, the atoms or the molecules are scattering light. So then you would measure the amount of light remaining after some of it's been scattered. And then there's the diffraction, which is a component in a monochromator, where you actually diffract the light into multiple wavelengths, and you use that to select a wavelength for particular absorption at a particular wavelength. And also, there are others that I will talk about later. For infrared, there is a different type of interaction that we'll talk about later. But these are the main ones. And then the most important one is which region the energy is being transmitted to that molecule or atom. And the region, it depends on where the wavelength of that particular light lies. So in food analysis, mostly it's either we're measuring absorbance or emission in the near UV, or in the visible spectrum, or in the infrared spectrum. Mostly food analysis is here. Now, NMR is down here, radio electromagnetic radiation. So, and then down here is the longest wavelength, and as you go up, gamma rays are the shortest. And the highest energy is associated with the shortest wavelength, and I'll explain that in a minute. Why you have the most energy with the shortest wavelength. I'll explain that. So this is kind of an overview of just how spectroscopy works, but we will go into details. So spectroscopy, there's different aspects of spectroscopy. You have the UV vis absorption, we have the infrared absorption, there is the fluorescence, which is emission of light, and then you have those specific for atoms, for element analysis, atomic absorption, and we're going to talk about ICP emission, which is inductively coupled plasma emission spectroscopy. You don't have to worry about the acronym right now, but it is measuring the emission of light by elements. And then we have the nuclear magnetic resonance, which will not be covered in this class.
What about X-ray?
X-ray, yes, but it is not commonly used for food application, but you do have X-ray analysis. I don't know, it's up here, right? But that would be more for medical.
So the metal detector on the production line is not an X-ray?
Oh, okay. Yes. Yeah, could be. And also you can do, there's another, you can do microscopy too, but that's a different than spectroscopy. Okay. All right. All right. And then mass spectrometry, this is the common mistake. And actually it was a mistake in the way it is listed in the book, current version of the book. It says spectroscopy, and under it all the chapters of spectroscopy, and MS is included. Now the new edition, it says spectroscopy and spectrometry for that section. Because spectroscopy is really different than spectrometry. Both gives you a spectra, but a different type of spectra. In mass spectrometry, it's a matter of forming an ion and by a certain energy, not light energy though. Okay? Spectroscopy, it's spectrophotometry, so it has light associated with it. So they're different. Okay? They both generate spectra, but different type of spectra. Okay, so I just wanted to make sure that you are aware of the difference. It's a big no-no to say mass spectroscopy. It's mass spectrometry. Never say spectroscopy, or you never say spectrometry is for MS. You don't say spectrophotometry. Don't say that. Okay. All right, let's list some applications where we use spectroscopy and spectrometry. You don't have that, Jeshu. So you have to think about application yourself. Hold on. Hold on, Aaron. Come on, guys. Throw anything in there, Bill.
Determining mineral content of dietary foods.
Yes, determining mineral content, quantification, basically, is one application. What else? What we, yeah?
Determining toxicology in medical foods.
Okay, so quantification, don't give specific application, give broad. So we talked about quantification. What else can you do with spectroscopy? What did we, spectroscopy, spectrometry, what did we do in the LCMS lab? What did we do, Michelle? Identification. So you can do quantification, you can do identification. What else can you do with NMR, for example? Yeah? Somebody is whispering something correct. Structural characterization, structural identification, elucidation of structure. Okay, what else do I have here? I can't remember what other application. Let me see. Peek. All right, so qualitative detection. In here, you just want to know, do you have it or you don't? Do you have pesticides in your sample or you don't? Identifications like we did in the LCMS lab. We identified the different isoflavones. Structure elucidation, that's what you would do in NMR when I gave you the example of elucidating the structure of the isomer. Quantification, like the example of toxicology or determining mineral amount, concentration, compositional analysis, quality assurance and forensics. So you use spectroscopy and spectrometry when you're searching to see what's in there and you don't know. So you look for chemical markers to identify kind of like what do you have that is foreign in your product. So it is widely used, very much used. That's why we are studying spectroscopy. Okay, so let's go take a step back and remind you of the physics of light. So, but not too much. I just want to introduce terms that you're going to hear. So light can have wavelike properties. It can have a pockets of energy property, and that's when you hear photon of light. And it can have a wavelike properties when you determine, for example, the wavelength or the frequency, and this is based on the wave-like property. So basically, a wave or a light wave, what will have, it has an oscillation of a maximum amplitude and the minimal amplitude. So, and then the distance between two maxima is your lambda, which is the wavelength. So the wavelength is between this maximum here and this maximum. And this would be a complete cycle. From here up to here, you have one wavelength. Okay? So you have the electric field and you have the magnetic field. And then the frequency is how many oscillations you have per unit time. Okay? So how many maxima and minima oscillation between maximum and minimum you have in a unit time. The more oscillations you have, the higher is the frequency, the higher is the energy. So in a unit time, the more oscillation you get is associated with the length of the wavelength, basically, the length of the light. So shorter wavelength will have more oscillations in 1 unit time than a longer wavelength. And that explains why shorter wavelengths carry more energy, have higher frequency. Okay? Anybody would like me to repeat that? Okay. So, I guess I explained all the terms here. So, wavelike properties also have something called interference, diffraction, and refraction. Interference is relevant when we talk about at near infrared and far infrared applications, and we'll talk about that later. But just to introduce what interference is for now, so that you understand what it means. So interference is when you have two wavelengths cross path in space. So they interfere with each other. If they cross path in such a way that the minimum overlaps the minimum and the maximum overlaps the maximum, you get amplification. And in IR, you use that a lot to amplify the energy that you give to the sample. So that is maximum interference in a constructive manner. You can have interference in a destructive manner, and that is when you have two waves interfere with each other in opposite ways. So the minimum here with the maximum, and the maximum with the minimum, you get cancellation. So if they interfere in space, they can cancel each other. But this is maximal destructive interference. You can get partial destructive interference. You can get maximal. Again, these two properties are used in IR spectroscopy to regulate the amount of energy that reaches your sample. Diffraction. And that is what we use to select a particular wavelength. So you will have a grating device where your incident beam will hit a grating device, and that will diffract the light, fractionated into individual wavelength light. You can use a diffraction grating, or you can use a prism. Prism can do the same thing as well. Refraction is what they use for refractive index. You're probably familiar with the refractive index, and it's one of the detectors we use for LC. So in refraction, what happens is, this is the incident angle of light when you have air, or the air, let's say, is medium 1, and water with salt solution is medium 2. So light hits at a certain angle, and then it refracts, change direction when it enters in a different media. And then depending on the solid content, the refraction changes. And that's why you can measure refractive index to determine total soluble solids, for example. Okay? But when we're talking about using spectroscopy to quantify or identify, it's mostly the property of photon. The photon of light is basically a pocket of energy that is carried by the light. So when we want to talk about absorption of light or fluorescence of light, it's better to talk about it in terms of a photon of light rather than a wave property. So the wave consists of pockets of energy, like I said, and they're referred to as photons. So the energy of a photon is basically this E equals H is a constant, Planck's constant, and this unit here is the frequency. So the frequency is directly related to the energy. So the higher the frequency, the higher the energy. So we talked about monochromatic light before, but do you remember what it is? I wish I brought the chocolate, Amy.
I'd be answering that.
Okay, Drew, go for it.
When one specific wavelength of light is selected for.
Yes, one specific wavelength of light. So it's mono, so one chromophore, one specific wavelength of measurements. So electromagnetic radiation composed of waves having a single frequency and wavelength. So when you have one wavelength, you will have a single frequency, which is the number of oscillations per unit time. Okay, so what about a monochromator? Similar to what you would have in a UV variable detector, or similar to what you have for those of you that did the AA today. What does a monochromator do? I just talked about that a minute ago.
It absorbs at a specific,
Doesn't absorb yet. What does it do, the monochromator? Sonny?
It filters.
It diffracts the light, right? I just showed you that. It diffracts the light into, light comes with a mixture of several wavelengths, multiple wavelengths. It just diffracts it and allows you to select one for, to measure absorption or fluorescence at a single wavelength. So that's what it is. So usually you have your incident beam. This is inside of a spectrophotometer. So you would have an incident beam. This is a mirror. It would reflect it into a grating system or a prism, and it will breaks it into multiple wavelengths, and then you have a filter that allows, with an opening that allows a single wavelength, and that's usually moves, so you can control how to move it up and down to allow for a particular wavelength up here or down here, on here, and a single wavelength or a very narrow range of wavelengths enter that slit. You can control the opening of the slit to make it very, very narrow or a little bit broad. Okay. What is a photon flux? Okay, you guys. Number of photons flowing across a unit area perpendicular to the beam of per unit time. So you would have a surface and then you have light, and you would measure how many photons are hitting a surface per unit time, per second. Brightness or radiant intensity. So the intensity is equal to the energy that hits a surface per unit time. And that you can control sometimes how much the brightness of light. Instruments allow you to control how much light you project onto your sample cell or cuvette. So again, here I'm highlighting that higher frequency is associated with shorter wavelengths. So if you can see here, you have more frequency when you have smaller distance between the two maxima, and that means you have more energy. And then as the wavelengths go bigger, you have less energy associated with it. So in foot analysis, again, I want to highlight that this is the area of visible light where we measure between 400 to 700 or even 800 sometimes is the range of the the range of the visible. And then above the violet, you have the ultraviolet radiation, that's UV absorption or emission. And then here you have infrared radiation. And in foot analysis, we use mostly this region. Radio waves is only for NMR application. Okay, So like I said, when we're studying absorption or emission, we have to, it's easier to understand it as a pockets of energy or photon of light. Okay, here's what happens when energy is absorbed. So when light hits, I'm just taking one atom here in a molecule. So you have an electron in a particular orbit. Depending on the atom you have, you can have one orbit, one shell, two shells, three shells, depending on how many electrons you have. So the photon of light will hit an electron in a particular orbit, and this electron is just going to be very excited now. It has a lot of energy, so it jumps to a higher orbit. So that's the excited state. This phenomena from here to here is absorption of the energy, absorption of light. So what happened is your atom, your electron, and by default your atom absorbed energy and became excited. But it doesn't stay long in the excited state. It's not natural to have a lot of energy. It wants to get rid of it to go back to its ground state or stable state. So it will give it up. Some atoms or molecules are able to give the energy back in a form of a photon of light. Others just dissipate heat. That's why some fluoresce, some molecules do not fluoresce. Okay? So not everything fluoresces. Fluorescence is when a molecule or an atom emits radiation after it got excited. Okay. So this is exactly what I said, is when a molecule is struck by a photon, it will absorb light and go from ground to excited. The change in energy is equivalent to the amount of energy the photon of light carries. This is very important. So the increase of energy that the atom or molecule get is exactly the same as the energy of the photon. So this is where it gets really tricky in terms of understanding this concept. But this is the concept that allows you to understand why different molecules have different spectra. That means have different range of absorbance. If you remember, let me draw this, and this probably will help in the explanation. So if you remember, we're just going to look at the caffeine because you all done the LC lab. So you have absorbance, and then you have your spectra. And then if you remember, you had kind of a hill-shaped spectra with here maximum absorption is at 272 nanometer. So here you had no absorbance at 230, for example, and here at 300 you had no absorbance. So the light has been projected on your sample, but it did not absorb. There's energy projected to it, but it didn't take it. That means that every atom and every molecule has allowable energy that it can consume. So that's what is meant by series of discrete steps. So it's not a continuous, it's not based off, if you give me, let's say, this bit of energy, I'll take it, and if you increase it a little bit, I'll take more. No, it doesn't work that way. It's not a continuous. If you give me energy I'm allowed to consume, I will consume it, and I'll show you absorbance. Okay? So that's why it is, you see absorbance here, you don't see absorbance here, you don't see absorbance here, which you would think, oh, but this is higher energy. This is higher energy than this. That is not related. Here I'm giving it higher energy at 230 nanometers, shorter wavelength, but it's not within its allowable units of energy that it can absorb. So it won't absorb it. Okay. And this demonstrated, but before I demonstrated looking at this figure, I just want to explain to you that the energy is either electronic, vibrational, or rotational. You have three different species of energy. Okay, so if we look at the electronic, this has to do by its name, the excitation that the electron gets in particular. So it's the energy absorbed by an electron that allows it to move from one shell to the next. So E is the electronic energy. So at this line you are at the ground state. Here you are at the first level of excitation, and then here's at your second level of excitation. So your electron can actually, it depends on which electron also absorb the light. Did the electron, if you have an atom, you have here, you have electrons here, and then electron there, depending on the type. Is the energy that was hit allows this to go up, or the energy allows this to go up? And the energy within these pockets are equivalent to the energy that the photons in the UV visible spectra carries. So electronic energy is very specific to the wavelength in the UV and the vis. I'm putting some of you to sleep. I know that. I can see some of you dozing off. I'm sorry, I don't like physics either. But it's part of the material, so bear with me. Okay, so UV vis is where it gives electronic energy. Vibrational energy is when you have a molecule. When you have a molecule, you have bonds. It would be between 2 atoms or 3 atoms or 4 atoms, depending on the molecule. So with that, the atoms are not sitting still. They stretch, they bend. So they're always in motion. And if you give them energy, they're going to stretch more or bend more. You're going to excite them. And the vibrational energy the pockets of energy are smaller than the pockets of energy of the electronic energy. So you'll see here, this is the first level of vibration, second, third, fourth, fifth. They're all within the first electronic energy level. So they're smaller. That's why they overlap here. So the energy that can cause a vibrational change is smaller than the energy that can cause an electron to jump to a higher excitation level. So the magnitude of energy that allows vibrational energy is within the IR region. And then to link this, I say smaller, right? IR radiation has shorter or longer wavelength than UV or vis. Longer, very good. Because IR radiation has longer, the allowable energy changes are smaller. Okay, so this is linking the wavelength to the energy, to the type of radiation that causes that change in energy. So do atoms have vibrational energy? No. Atoms do not have vibrational energy. So those of you that did the AA today, we did what kind of absorption and which level, atomic or vibrational? Atomic. We broke all molecules into atoms, and then the excitation occurred due to electrons going from a ground state to an excited state from one orbit to the other. The rotational energy, this is when your molecule rotates around its center of gravity. What allows a molecule to rotate around its center of gravity is an energy equivalent to microwave radiation, which is longer wavelength, so it's associated with smaller amount, longer wavelength, less amount of energy. That's why it overlaps. The increments are smaller than the increments of the vibration, and obviously smaller than the increments of electronic energy. Microwave spectroscopy is not of interest to food science, but it's part of the energy, so therefore we learn it, but we don't care for it. So, energy state of matter, so you have the atom has only electronic energy. The atom, so if you have an atom, you only have electronic. Molecule, you have three types can happen: electronic, vibration, and rotation. So if you have a source of light that allows a range of light from different wavelengths, it can give you infrared, it can give you UV, visible, or it can give you even microwave. You will have a molecule that can go, for example, from here up to here, or from here and cross the first electronic level, the first vibration, and reaches the rotation level 4, for example. Because this source of light allowed different amounts of energy to be delivered for a molecule. So, because the associated energy is quantized, yes, so it is a discrete sizing, you will have different species will have different energy spacing. So that's why you will have a species that will have allows certain absorbances, and then another species that have something like that, allowing different absorbance. For the same light, you will get different excitations for one species versus another species. Oh, it's right there. Okay, this is the example where you have this one species and then another has different wavelength excitations. So the emission of light, we talked about it briefly, but it's going from excited state to ground state, so that calls the relaxation. Not all molecules can give back photons of light, only those that fluoresce. So you can use fluorescence spectroscopy with that. So basically your electron goes back to its regular shell, and the very key thing that happens is while the electron is going back, there is some dissipation of heat at the same time as the release of a photon. So not all of the energy is released as a photon in fluorescence. Part of the energy is lost as heat, and part of the energy is given back as a photon. As a result of that, always, your emission wavelength is longer wavelength. Longer means less energy. So when you are reading a method for measuring fluorescence, you're going to say, okay, absorption, so we set the wavelength at, let's say, 304, and then we measured fluorescence at 340. So that you have to set at a particular absorption that allows absorption of light, and then you have to monitor emission at that amount of energy that's going to be released. So there is always the absorption wavelength, and there's always the fluorescence wavelength. So when you're setting up a method for fluorescence, you have to always set it up so that you have a monochromator that selects the light hitting the sample, and then a monochromator that selects the light that is emitted from the sample. And it's always longer wavelength because you always have less energy. Again, because part of the energy is dissipated as heat. Questions? done with this lecture. Yeah.
I wanted to double check with you. You talked about cancellation. It's when two wavelengths, they have basically opposite minimum and maximum.
Yeah. Yes. And they hit the space in the opposite minima and maxima hits the same space in the opposite. All right. Giving you 7 minutes early. Goodbye.